Hi guys, so today we'll be doing Leetcode daily challenge, hide a binary tree after subtree removal queries. So long thing short, we are given a binary tree and then a list of queries, right? We need to return an array of answer size m where answer I is the height of tree after performing the ith query. We performing the ith query by basically remove the subtree root at the node with the value queries I. So let's take a look at this example. We are given a binary tree. We are given a list of queries here 4, right? So we remove this subtree entirely. So what is the depth? The depth is 2 basically, right? Take a look at this example. We have this binary tree. We have this queries. So we remove 3. And then the height is basically the same 4. So if we remove 2, the height is actually going to be reduced, right? It's going to be 2. So now if we are going to remove this subtree, the height is the same. Remove this subtree and then the height is going to be 2, right? So how are we going to approach this problem? We need to take into consideration of every possibilities when removing a subtree, right? So if we remove a subtree, right? Let's say that we remove a subtree and then we still have elements node on the same level, right? Then we are going to take the node with the max depth on that level and then append it to the result, right? That's one possibilities. And then what else? If that node is simply the only node in that current level, then we are going to just return the previous level, right? The current level minus 1. Let's say that we are going to remove this node, right? Because there are no nodes on the same level, we are going to simply just return the current level minus 1. Okay, so that's 2 possibilities. And how are we going to do this problem? Basically, the approach is that we're going to use map, right? We're going to use map to store the value of each node with the max depth of each node, right? And then that is going to be the max depth map. Let's call it depth map default tick of int. And then we are going to store the information on the node of the same level, right? Basically it's going to be 0, 1, which means on level 0 we only have node 1. 1 and 3, 4 basically mean on level 1 we have node 3 and node 4, and vice versa. And then when we basically when we deal with a query, we're going to take a look at every element on the same level and then take the maximum depth of every node, right? We take a look at every node and return the maximum depth. But is that going to be efficient enough? Probably not, because on a tree with a large size tree, then basically that's going to be roughly log 2 of the size of the tree, which means right? Okay, so if we have basically a tree with 4 level, that's basically going to be 2 to the power of 4, 2 to the power of 3, right? Node that means 1, 2, 3, 4, 5, 6, 7, 8 right? 8 node, right? So with subtree with log subtree with like also large level, that's basically going to be really inefficient, right? So how about we are only going to store the 2 max step at each level, right? That's going to be O1. If we look it up, and it's going to be O1 only, right? And it's going to be really efficient. So let's say max step at each level is going to be default dict lambda -1 we are going to store the 2 max step at each level, right? And then we basically have to have level map also. Why? Because we are storing the information of the depth, right? We need to store the information of the level also, because basically for a node, then we need to return the depth. We are storing the depth, means the depth from that node onward only, right? But we need to append to the result the depth from the root of the tree till the end, and hence we need to store the information about the level of each node. And then now how are we going to populate these 3 dictionary, right? We can populate it using a simple div-s traversal technique. Div-s root level if not root, which returns 0, else the max step will be equal to max div-s root at left level +1 div-s root at right level +1 and then let's say that map root val is equal to max step, right? Okay, so level map current level root val is equal to current level, and then we are going to update the max step at level. So basically, if max step is larger than max step at level current level 0, then like this. If the current max step is only larger than second values only, then we are going to update that value only, right? Okay, so now don't forget to propagate this information upward, so we can use that information in the parent node, right? Okay, so we can print out the map to see if we have done it correctly. It's level, right? It's level. Okay. Okay, we have the depth map. 2 is 1, 3 is 2, and that's weird. Here's the max step at each level. 0, 4, -1. Okay. 3, 1, 0, 1, 2, 3. 3 we have 1 and -1 because we only have one node at this level, right? Here's the depth map. 2, 1. What are we going? Depth map. Okay. 2 is 1. 3 is 2. Okay. I think that's correct, right? So now, what are we going to do next? And then we are going to say for Q in queries. Okay. So we have current level is equal to level map of Q, right? Basically, we're storing the level of each node in the level map dictionary, and then we are going to say the max step and second max step is equal to max step at level current level, and then if max step is equal to -1 or second max step is equal to -1, which means on the same level of this node there only one node, right? So basically if we remove this node then basically there's no node on the same level, so we just return we're just going to say resolve this, resolve this append current level -1, right? Else we need to compute the current max step, which is depth map Q, right? And if current max step is equal to max depth, then we're going to say resolve append second max depth plus current level -1, else resolve append max depth plus current level -1, and then we'll just return result. That's basically it. Okay, run the queries. Okay, so as you can see, it's very efficient. So time complexity is O(n). Basically, we only need to do a DFS, which is O(n), and then for each query, let's say the size query is m, so that's O(n) plus m, because for each query then every lookup here is actually O(1), right? Even the current max step lookup is O(1) only, because we are basically storing 2 values per level. And then the space complexity is O of n. Let's say plus n, because the result is m. Okay, so that's it for today. So I hope that you guys understand the solution. This is basically this not hard, right? This is not hard, but and does not require advanced algorithm, but you need to understand very thoroughly about binary tree, and then how to use hash map efficiently. Overall, this is a good problem to practice your implementation and also your logical thinking. Okay, that's it for today. So I'll see you guys in next video, and thank you for watching.